was a pretty reasonable first effort. The average percentage wise was around 66 or something like that. I've uploaded your grade. You have any questions about the grading or one of the best exercises you can do after an exam, I think, is this. Go through without the pressure of having to sit there and take the test and see if you can work through the problem yourself. If you're hung up on it, then come see me. And also, here's my rule. I don't want you to be afraid about asking about stuff. So you can ask about the grading, whatever. If there's a mistake in the grading and it's in your favor, you will not be punished for that. It's your lucky day. So I don't want you all to be shy about things to see about that. Okay, questions? All right. So what we're going to do today we're going to talk about determinants. Now we sort of know what this is because we've looked at this. We defined this for 2x2 matrices. Y'all remember this on quiz, class, but I had really didn't explain to you how the world was that you would do this for something bigger, and now we're going to discover that. So here's kind of a so let's kind of decide what a determinant should be for a 3x3. Okay, and this is just me kind of playing fast and loose here to figure out what should be going on. Now, does anybody remember what the big deal was about 2x2 determinants? Right. So if you had a 2x2 matrix, and we call this A. This here was the determinant, and sort of what was the big pivoting value from zero? The determinant for the determinant was zero, wasn't it? Right. And if the determinant is zero, then the matrix was single, right? And if the determinant was not zero, then you can invert the matrix, right? What else do we need to be able to invert a square matrix? We need that every column is a pivot, right? Everybody agree with that? That's what we need to have an invertible matrix. So let's try to emulate that here. So let's consider matrix. I don't use subscript letters here. I want to hear it this way now. Let's say P, Q, R, and base. Okay, so what I'm going to do is I'm going to try to come up with an idea of what a determinant should be. And here's my basic philosophy. For a 2x2 matrix, the matrix was invertible if and only if that determinant was not zero, right? So the matrix was not, so another way to put this is is not zero if and only if this has exactly two pivot columns. Right? Because if it's got two pivot columns, we can reduce it to the identity. Right? Okay, so let's see what happens if this has to be three pivot columns, right? So my goal is I want three pivot columns. Right? Well, would everybody agree that one of these entries in the first column has to not be zero? Because if that's a column of zeros, I'm already hosed. So, right? So let's suppose that A is not zero. And even if it is zero, I could just turn the rows around and make sure we get left. Right? So what I'm going to do is I'm going to row reduce this. And I know this is a kind of obnoxious, but what I'm going to do is I'm going to use this A, get rid of B and X, and I can do that because A is not zero. So I'm going to multiply this top row by negative P over A and add it to this row. Right? And so what I'm going to get here is 0 I am going to get Q minus P over A, V and R minus P over A, C. Super obnoxious, but that's what I get. And I'm going to do the same thing down here. I'm going to multiply this minus X. I'll multiply this by minus X over A and I'm going to put 0, which is the whole point, and I'm going to get Y minus X over A, B, C minus X over A, C. All right. How many of you think this one's yet? Yeah, it's awful, isn't it? But let me do something here just to make this a little bit cleaner. I'm going to multiply, since A is not 0, I'm going to multiply middle row and this by A, just to kind of clean it up a little bit. And so it's still going to be yucky, but at least I won't have fractions. This is going to be Q minus PB, or I'm sorry, QA minus PB. And this is going to be RA minus PC. And I'm going to multiply the bottom row by A. And again, I can do this because A is not 0. I'm going to get YA minus XB. And I'm going to get CA minus XC. Now, this is not 0 here. Now, if I want this to have 3 pivot columns, then one of these is, we can't have all of these be 0, right? So let's assume this one's not 0 again, and row reduce it further. And if I row reduce this further, say that I focus on this right here. Assuming this is not 0, then I can divide by this and take this out, right? And it's going to make a mess here. So what am I going to have to do? I'm going to have to multiply this, take this out. I'm going to have to take this row and multiply this by Y over A minus X over B, QA minus. So you don't need to worry about too much of this stuff here. The whole point is what happens to this QA minus BC? It cancels out. If I agree, when I multiply this by this, it cancels out. Then I have this negative thing that I added this down here, and I'm going to get a 0. Everybody okay? Yeah, what a mess, right? But I'm going to get a 0 here, and the question is, what do I get here? And at this point, to have 3 pivots, I need this to be not 0. Everybody agree? So really what I want is I want this last result here to not be 0. So for 3 pivots, I want whatever goes down here, not 0. So what goes down here? Well, what goes down here is this thing. XC. Minus AY minus BX over AQ minus BB. Times RA minus BC. Yeah, I know it's horrible, right? But really what I'm saying is this thing times this, subtracted from what this was, I want this to not be zero. Everybody okay with this? Now, this thing is not zero because it's in a denominator. So let me multiply this whole thing by a cubed minus BP. And multiply this whole thing by this. And so I get a cubed minus BP times this mess minus AY minus BX times this mess. Right, and this just multiplying both sides of the denominator, clearing it out. Right, now, this looks like I'm eating alphabet soup here, but let's clean this up a little bit. So if I multiply this out, I get a squared QZ, multiply this, I get minus a QXC, multiply this, minus BPCA, plus BPXC. Then I'm going to multiply this out. Be careful, there's minus in front. I get minus a squared YR squared YR plus AYPC. And that will be plus N BXRA. And finally minus BXPC. And I'll make it no. Anybody see anything that we can do? This is horrible. I got 2, 4, 6, 8 terms. Anybody see anything? Yeah. Very astute. These two kill each other, right? So it's a little easier now. So what I now get is a squared QZ minus AQXC right, minus BPCA minus a squared YR plus BYPC plus BXR. And actually, just for keepsakes here, let me write my root matrix here. A, B, C. Anybody see something else here? Let's see something else in my help. Yeah. It's like every day. There is a common factor of A here. Everybody agree with that? So pull that A out, and A times whatever origin of letters is left over. A times that is not zero. Since A is not zero, this means that A QZ minus QXC minus BPC minus AYR plus YPC plus BXR. Because A is not zero. Now I want to do a little bit of sagacious grouping. I'm going to group this together. So I'm going to pull these two out first. This is going to be A times QZ minus YR. And I'm going to group these together. I'll put a little X over this. I'm going to pull a negative B out of that. PC minus X bar. And finally, I'm going to put a little circle over this. Looks like this has got a common factor of C. YP minus X. What a mess. But does anybody see? So I've got A times something, I've got B times something, and C times something. Anybody see what, anybody recognize what these are? Yeah.
It's like some 4x4 matrices in that.
You mean 2 by 2, but yeah. Right. So if you look at that A, it's QZ minus YR. So if you omit this row and column, the QZ minus YR will determine that little submatrix, right? If you look at what's multiplying B, it's PZ minus XR, which is the determinant of that matrix. It's off by sign, but it's the same thing. If you look at what C's multiplying, it's PY minus QX, right? Right. And this is actually this thing right here is what we want the determinant of this matrix. Yes.
When would you use that versus just row reducing with the identity matrix? The other method.
Because we're actually trying to find the determinant. We're trying to find intelligence in what the determinant is. And actually, you're going to use the determinant for things like Kramer's rule, and it actually shows up quite a bit. It shows up in everything from modeling, for example, the aerodynamics of an airplane to number theory, from the very theoretical to very practical. The determinant is a very important tool. So let me tell you how to do it. And then I'll do some examples. The determinant is defined the way that we call, I would say this is defined inductively. So the determinant of a larger matrix is in terms of determinants of smaller matrix. And the following, let A be a matrix. When we discuss determinants, we are always talking about square matrices. It has to be a square matrix for us to discuss this. We'll say that A is Aij. So this means these are the addresses, the coordinates, the ith row, j column. Then determinant of A is equal to A11 determinant A11 minus A12 determinant A12 plus A13 determinant 3. Finally, minus 1 plus n determinant A1n. Now, I haven't told you what these followings are. By the way, I'll write this in a single point. 1 minus 1 to the 1 plus j determinant of A1. Now, I haven't told you what this is, and this is what makes determinants a little bit. They're not bad for small values for n, for small size matrix. But doing this computation gets out of hand pretty quickly. Where A1j is determined of matrix is the matrix obtained by deleting first row and j column. Okay, so let's look at an example. Let's actually compute some of these. So let me start with a 2 by 2, and I'll do a general formula for that. Let's go through the formula. What the formula says is take so what does the formula say? It just says read along the top, first row. It should be A times determinant of the matrix obtained when I delete first row of the first column. And you just get a 1 by 1, right? Can't beat that with a stick. Minus this row or this entry times what's left over when you delete the first row, second column. And I get A, D minus B, C. Yay, so it works. 2 by 2. Okay, let's up the voltage. What if we have something like this? We have 3 by 3. Well, what this formula says is the determinant of A is equal to this row or this entry times the determinant of what's left over when I nuke this. So this should be 5, 6, 8, 9. Right, okay. Minus, okay, now we move to this one. Okay, I need to figure out what the matrix is when I move the first row and second column is 4, 6, 7, 9. Right. And now back to plus with this one here. When I move the first row, third column, I get 4, 5, 7. Agree? You see now, what we've got is to work this determinant. We've now got to work 3 small ones, right? And you better pay attention to my arithmetic here and make sure I don't screw this up. But the determinant of that first one should be 45 minus 48. Correct. Minus 2 times this determinant. This is 36 minus 42. So that's going to be minus 6. And finally, 3 times this determinant is 32 minus 35, which is minus. So what is this? This is minus 3 plus 12 minus 9, which is 0. Yes,
Does that work for all matrices or just squared matrices?
there is no determinant. It's not squared. You have to discuss determinants, you want all the matrices. Yes.
So it has to be squared because why?
It has to be squared because otherwise the algorithm is not defined. To have a determinant, it is only defined for square matrices. Now, if you want to go out and try to define one for, I mean, you can always do something like this. Right? If a matrix is not square, you can fill it in. So if you have a matrix like this, to define a determinant or something like this, you can always add column zeros, but you're always going to get zero. It's determinant anyway, right? And there are other functions that you can come up with, multilinear functions or something like that, perhaps. But the determinant is just defined on square matrices. That's all we're going to work. That's all we're going to focus on. By the way, any ideas on what might happen if we row reduce this matrix? What's that? Okay, so let's see what happens. One, two, three. Okay, I'll put my minus 4 and add. Minus 4 and add. Minus 4 and add. Times minus 7 and add. Minus 7 and add. Minus 7 and add.
Yes.
What can you say about this here? This is actually negative. If you multiply this by -2, you get this. So there's going to be less than 3 pivots, right? So this matrix is not invertible, right? Because there's less than 3 pivots, 3 by 3, and the determinant turned out to be 0. That's a big number. Let me do kind of one more example here before I sort of get out more serious. Well, let's let A. And I don't know if I'm going to finish this problem or not. I'm not sure I'm going to finish this problem, but I'm going to set it up just to show you what obnoxious mess this is. How do you do a 4 by 4 determinant? Yes.
You would do the same thing, so you would take the A and multiply by the bottom right, 3 by 3, like the net bottom right. 3 by 3.
That's exactly right. So, So what we do is we just follow the formula again. So you just move across the top row, and it's 1 times determinant of the matrix you get by nuking the first row and the first column, which turns out to be 1, 1, 1, 4, 1, 3, 1, 0, 1. Oh, I got lucky. Minus 0 times determinant of. And for completeness, I'll write this down, but of course I'm going to get 0 here, multiply by 0. But if I do first row and the second column, I get 0, 1, 1. I get 2, 1, 3, and I get 0, 0, 1. Plus, minus, plus, so that's going to be minus 1 determinant of what I get when I do the first row and third column, 0, 1, 1. 2, 1, 3. No, 2, 4. And 0, 1. And finally, see, plus, minus, it's going to be minus 1. Now in the first row and third column, I get 0, 1, 1, 2, 4, 1, and 0, 1, 0. Everybody okay with that? So now, I want to, of course, this one is gone, right? That's convenient because it was a 0 there. But still, now I have to go through and work out three 3x3 determinants, right? And you can do it, and that's the answer, but it's complicated, right? So I'll let you finish this exercise. Let me give you let me give you some motivation for this. Matrices are used all over the place. They're used in, for example, image processing. They're used in data mining. When you do a Google search, there's a matrix being used. I saw a plane flying over the hurricane today, and I hope it works out because they do the aerodynamics on that. They model that with differential equations, which gives rise to a matrix, sometimes several 100,000 square by several 100,000. These are important objects to work with. They're very complicated. Using this algorithm that I've described to you, how long do you think on average it will take a computer to compute the determinant of, say, let's be modest, a 40 by 40 matrix?
Probably like 50 volts.
Let's assume your computer does 1 trillion operations per second. So it can do 1 trillion operations per second. How long does it take?
Well, it's like going down like one size per thing, so if you like. I don't know the exact formula, but it's like, is it an exponential? Like,
It's worse than that.
It's worse than exponential.
Yeah, it's like a So to just kind of do our definition and just go through this, go across the top and do these computations and just, okay, now I go from a 40 and then I have to compute 39 by 39 matrices, and every one of those have to compute 38 by 38 matrices and so forth and so on. If your computer can do 1 trillion operations per second, it will take about 1.8 billion times the age of the universe to compute the determinant of a 40 by 40 matrix. This is motivation for us to maybe think about some other ways to do this, right? This is why, by the way, a brain is better than a computer, always. Okay, so here is, let me give you kind of the first sort of way to get around this, and it would probably be a better way to do this matrix here. Let me give you a definition. Let A let's suppose that you have an n by n matrix defined that way. So this is A1 all the way over. Then the IJ cofactor, which I will note Cij is the Cij that I'm going to find, we'll call the IJ cofactor is the following number. -1 I plus j power determinant of Aij. And again, I'm going to tell you what Aij is, but it's what you would expect, where Aij is matrix obtained by deleting the ith column in J's row. So this is what the cofactor is. And let me tell you how the cofactor will step in for us here. There. Let's let AIJ and here I guess it can write this out. Let's do it. You can see a little bit better. Okay, so suppose we have a square matrix like this. Then determinant of A can be computed. Along any column or row of my code. So let me make that precise. Let me give you an actual point to use what I mean by this. So here's a couple options. Determinant of A is I1 CI1 plus I2 CI2 AIN CIN. So if you go across, notice the I is always the same here. So this is expansion about the ith row, or you could expand by the J column. So you have the luxury of being able to sort of expand this about any row or column. One J, C1J, A2J, C2J, plus ANJ, CE. So let's look at this. So for example, short example, then you'll need on it. Let A be 2, 4, -5, 0, 2, 0. Okay, let's suppose we have this matrix, right? Right, and I want to know what its determinant is. It's important. Maybe I want to know if the system is, the system has more than one solution or something. Now, this theorem gives us the power to expand about any row or column. What column or row looks best to you here? The second column is looking really good because it's almost all zero, right? What this says is we can expand so let's do this. So this would be determinant of A. So let me adapt the formula here. This is about the second column. So this would be A1, 2 cofactor C1, 2 plus A 2, 2 C2, 2 plus A 3, 2 C. Now I'm expanding about this second column. So take the 1, 2 entry. First, for the sake of almost 0. A22 is A22, C22, and A22. And all of a sudden, our work is so much easier. So all I have to do now is this is 2 times C22. So let me take a little aside and figure out what C22 is. Well, let's see. It's -1 to the 2 plus 2 times the determinant of the matrix I get when I do that. Take out the second row and second column, which in our case is 2 minus 5, 1, 3. So this is going to be +1 because it's an even power. And the determinant of this is 6 plus 2. That's much easier than having to do a bunch of things. Yes.
So it only really helps if you have scales, the matrix.
What's that?
Does it only really help if you have scales in the matrix?
No, because sometimes what you can do is if you notice that if you move the row or column, that one row is a multiple of another or something like that. But I'll get to that later. But yes, it is most helpful when you have zeros. But actually, matrices with lots of zeros in them actually do show up in a lot of applications. They're called sparse matrices, and it can so in that sense, this can be very helpful. So let's do this. Let's determine it. 17. 1, 5, 3, 2. 0, 0, 1, 0, 0. 0, 1, 2, 1, 0. 0, 3, 1, 0, 1. And 0, 0, 4, 0, 2. So I really like the second column here, right? I'm sorry, really like the second row. The first column looks good too, but I'm really liking the second row. You might try to check me by expanding about the first column and see if I got this right? In there. So it's like I got that right. So it's going to be expanding about this, and we'll get 0, 0, 0. So what it's going to be is, I call this matrix A, it's going to be -1. Let's see. Well, it's going to be A. Let's see, it's going to be second row, third column. So this is going to be A23 is 1, and this cofactor is -1 from 2 plus 3, so that's going to be negative, times the determinant of what I get when I remove this row of this column. So that's going to be 17, 3, 2, 71, 3, 2, 0, 1, 1, 0, 0, 3, 0, 1, and 0, 0, 0, 2. So now let me take this one let me take a little aside with this. So we get this determinant. 17, 1, 3, 2, 0, 1, 1, 0, 0, 3, 0, 1, 0, 0, 0, 2. I'll expand about. Fourth row. And so the determinant of B is A 4, 4, 4 row, 4 column, times C 4, 4. Which is, in our case, 2 times minus 1, the 4 plus 4, times determinant of what I get when I do this row in this column, which is 17, 1, 3, 0, 1, 1, 0, 3, 0. So let's add this bit here. So this is going to be negative. It's going to be positive. So this is going to be negative 2 times determinant of 17, 1, 3, 0, 1, 1, 0, 0. And so finally, I guess I need that last determinant. And the last determinant, 17, 1, 3, 0, 1, 1, 0, 3, 0. I'm going to expand this about the last row. So this is going to be A, in this case, third row, second column, becomes C32, which is 3 times minus 1 to the 3 plus 2 times the determinant of this matrix here. So that's going to be 17, 3, 0, 1. So this is going to be minus 3 times 17. So I think this is signed here. I get minus 2 times that determinant. So it's going to be 6 times 17 is 102. Okay. Any questions? Let me give you one final theory. And I'll let you puzzle on this for next time, but this is really cool. There. Okay. Fine. Upper or lower? Then, determinant of A is product of diagonal. So, let me go ahead. Let me make this right. This is an upper triangular matrix. The determinant of this is product of diagonal 4, 3, 5, 1, which is 6. This is also true for a lower diagonal matrix. Determinant of this is 6. see if you can get that, and if you were to sort of prove this is true, just expand about this first column, and you will get that as you keep going, you get all the diagonals. This is actually, in fact, this is a big takeaway. So you were asked about how to do this quicker. The determinant of an upper or lower triangular matrix, just read the diagonals and multiply them. And so if we can turn a matrix into that without affecting the determinant, that's the best way to go. And we'll talk about that next time. Any questions? I encourage y'all to be at the math club today. Other than that, y'all have a good weekend and stay real. Yes.
So for when you did the 1 and 2, did that one, and then you moved on to like the negative 13 times 7, where did the 1 and 2 go?
So, this is negative 2 times this, and that turned out to be like negative 3 times 17, right? So that 2, it's multiplied by, this thing turned out to be 3 times 17.
Oh, so you solved that.
Right, yeah, so I did it kind of in chunks. Sorry about that.
Okay, go ahead.
You have the answer. The one that-
Pretty sure. No, I don't. I kind of made it up on the fly, but if you like it, we'll do it. My suggestion for you is do row operations and reduce it to an exercise.
Oh, no, I just did it all.
Which is. Yeah, that sounds pretty easy. Joey? Right. I'm sorry, I didn't answer the person. That's enough. Did you have any questions?
No, but I.
Okay.
Thank
Yes.
I'm gonna emergency 4 hours.
I made a choice to expand about that road, right? And all these zeros are going to 0 times determinants going to be gone. So it's going to be 1 times what's left over when I move the row 1 and the column, or the row 1 is the column. Right? And then I pass down the smaller matrix. You can see that's the magic of that. You can choose any row or any column to expand by, right? You can go by the last row or middle column or whatever you want, and that formula will work. And I chose that second row because it was so full of zeros that it made my life easy.